Good morning, guys. I'm gonna knock this video out first thing in the morning. Kids are playing Legos and Tangos, and hopefully they won't hear me talking and what are you doing and start jumping in front of the camera and acting crazy. So I'm actually gonna just try and speak from the book because my computer is dead. I normally take notes and speak from my notes. So hopefully I don't look like I'm just staring at the book. That's not what I want to do. That's not very entertaining for you to watch. I thought I might also look for some Khan Academy videos on this topic too. Because as I started reading it, I was having flashbacks to physics, and I really like physics. It was just really hard for me. Something about the way my brain works doesn't seem to mesh well with physics. So I don't think I'm a very spatial thinker, and this is not spatial, but it was a lot of physics. It was just reminding me of that. And I thought, I don't know if I'm capable of teaching this. I think I am though, so not to fear. Okay, so you guys would laugh if you could see what I'm using to hold my phone. It's one of those big white styrofoam coolers. And it's got little cup holders at the top, and they're like just the right height and hold your phone really well. So you just never know what will work. Buy something expensive or use my styrofoam cooler. Okay, so module 12, we're talking about energy and heat and temperature. And we've talked about some of those things along the way, right? So some of this, it's new, but it's not. And if you've taken physics, you've probably already covered this. So I feel like one of you is taking physics. Maybe I'm wrong. No, you can't be taking physics at the same time. So it's probably new to all of you, but you probably encountered it like in your physical science class maybe. So energy, and I know that Mrs. Dunn, no, I was thinking she did. Never mind. I'm just gonna stop talking. We'll just talk about module 12 because that is what matters. Doesn't matter if you've heard about it before or not, but if you have, it'll help. So we've talked a lot about energy, but I think if any of us tried to say what actually is energy, we might have a little bit of difficulty if we haven't encountered a definition already. Energy is defined as the ability to do work. So then the question is, what's work? If you pushed against a wall and the wall did not move, you wouldn't actually have done work. Because work requires, it's the force applied to an object times the distance that that object travels parallel to that force. So if I am pushing a rock parallel across the ground, the force of me pushing times the distance that object travels would describe the amount of work that I did. So energy is just the ability to do that work. So energy requires a force and it requires movement. And so then the book begins to talk about, what is fire? Fire is energy. There's energy being released, and is there any movement actually happening? And it's talking about the movement of the flames and the movement of the smoke, and there is actually movement going on. Not movement that you would think of in terms of parallel to the force, but like pushing that rock. So a little more complicated, and that's when that gets in more into physics, but just to demonstrate that there's movement happening there. And then they talk about heat, and heat is just energy. It's just energy that's transferred as a consequence of differences in temperature. And so heat always travels from hot to cold. Something that's cold is absorbing the heat. It's not giving away its cold, if that makes sense. Heat is the actual energy. So something cold will absorb heat from the environment or absorb heat from something else. I think I was trying to tell you that earlier, and I didn't say it very well. I don't think I had the words to say it properly. Or at that time, I wasn't saying it very well. But that's what I was trying to say, is that the heat is what's being transferred. You never transfer cold. Cold is just the absence of a certain amount of heat, if that makes sense. So heat is energy. Okay, I think we covered everything there. So I'm just looking to see what they talk about next in the book. There's a lot of discussion in this chapter. Here they're starting to talk about potential energy. They're saying, oh, well, if there's energy in the wood, why, if I just have my wood sitting out in a wood pile, doesn't that heat me? And we're going to find out why that is. But they lead into the first law of thermodynamics, and it's kind of like mass is not created or destroyed. Energy cannot be created or destroyed. It just changes form. So all the energy that's in the universe was here from the beginning of time. And there's not been any more added, which is kind of incredible when you think about it. Like think about things like an atomic bomb. All the energy that exploded from that atomic bomb was already here in the universe. We didn't create all that energy out of nothing. And I think it's also interesting too when you go back and think about just being a thinking person. So you think about the origins of the earth. A lot of people who don't believe in a creation story or an intelligent design, the Big Bang Theory is a pretty commonly accepted theory. It keeps getting revised and as new information is found. But something I found interesting is just, well, where did all the energy come from that? Because the first law of thermodynamics is a well-accepted law, but then that would be negated in the creation of the universe because, at least from my understanding, I'm not an expert in this subject. If anyone comes along and listens to this video that's smarter than me and they may have some commentary on it, but I do think it's something to think about. It's easy for me to believe that the Creator God could create all that energy because he could do anything, or that he is all that energy, or whatever that might look like. But for it to come from nowhere is a little bit hard for me to believe, because if there's no energy, there's no energy. So where did all the energy come from? Anyway, just food for thought on the first law of thermodynamics and origins of the world. So one more coffee. Oh, you can't read that because, maybe it'll flip it. Delaney got this for me for Christmas. Everything gets better with a good book. I would agree. Okay, so we start talking about potential energy and kinetic energy. So I'm sure you've probably heard this. I know like the little kids just did like posters of their roller coasters. So they're at the top where they have all the potential energy, and then as they slide down, that energy is released. I think I said that right. Oh, I'm so bad at physics. But let me at least give you a definition. I think it's easier to understand in terms of wood. I always have a hard time thinking about it in terms of motion. Potential energy is energy that's stored. All that wood, it has all the potential for fires, right? But it's not being burned yet. It's not being released. Kinetic energy is energy that's in motion. So we have the force applied and we have movement applied. We get motion. We get energy. Let me see. I want to see. And so again, with that fire, there's no created energy. We have all the potential energy in the wood. It's just stored there. And then when it's released, we see the kinetic energy. Kinetic means movement, like kinesiology is the study of movement of the body. I don't know, I think that's a Latin root, not a Greek root. I would assume it's Latin. I don't know why, I just think it is. Let's see, and so heat is considered a type of kinetic energy. I want to see if there's something else that was clarifying with that. This says all substances have energy stored in them, so all substances have potential energy. That statement made me start thinking, like, whenever someone says all, I start thinking, everything? Not because I know something, but I was trying to think, like, do rocks have potential energy? Or, I feel like all organic things might have potential energy. I want to do a little more research on that. I'm probably wrong, but I like asking questions. You know what? When you ask questions, don't worry about whether you're right or wrong. Just ask questions, because you might stumble upon something, and or they might get it corrected, and that's fine too, because then you just have a better understanding. So ask questions. Don't worry about whether, oh, that was a dumb question. I might be wrong. Rocks very, very well. I mean, like a rock as a solid thing, like sitting at the top of like a big hill. I guess it could have potential energy just because of its mass. And then as it rolls down, the energy is released. That might be, you can't burn it. Might be in terms of that. And that might be why, just in terms of its mass, that can start a force. That's probably what it is. Okay. I think out loud. That's not very helpful to you, I'm sure. Then we talk about units for measuring heat and energy. And so in the metric system, we measure energy as joules. So if you go back and remember, what is energy? Ability to do work. What is work? It's the force applied to an object times the distance that the object travels. So it's almost like a Newton meter. Force is measured in newtons and distance in meter, a Newton meter. But we also call energy a joule, named after a scientist, James Prescott Joule. And that's pretty commonly accepted. You'll hear joules when you're talking about energy. And that's the metric unit for energy. And so to give you an idea of how much energy a joule is, lifting a 102-gram object straight up at a constant speed for a meter. That's 1 joule of energy. 102 grams is like, what did I say? Like a paper clip is like 1 gram. So 102 paper clips. So it wouldn't weigh very much. 102 grams doesn't weigh very much. So 1 joule isn't a ton of energy, but that's how we define it. That gives you a picture of what that is. And measuring energy is a little tricky. Measuring potential energy, I don't really know how to do. And as they say, it's beyond the scope of this book. I think probably even a basic physics class, I think. I don't know a lot about how to measure potential energy. I would have to do some research on that. And we're not going to do that in this class. But we are going to measure the change in heat because heat is energy, and we can measure that indirectly with temperature. So the temperature isn't exactly the energy, but the difference in the temperature tells us how the energy is changing. So it's an indirect measurement, which, as they know, we do that a lot in science in general, measure something indirectly to tell us about the thing we actually want to see. So they talk about how a thermometer works. I just thought this was so ironic. So much conversation about thermometers with all our broken thermometers in our lab that we need to replace. So it talks about a thermometer makes use of substances that kind of expand as they get warm, and then they move up. And so again, it's indirect. It's absorbing heat. So it's absorbing that energy, and it's changing as that energy changes, or as that heat decreases. So that's that indirect measurement. And then they have a really long lab on calibrating your thermometer. I don't know if we're going to do that one. I'd really like to find a lab that's really exciting, because I don't feel like we did do the one fun one with the cabbage leaves and things changing color. I think that one was fun. But I'd like to find something that's kind of exciting. I'm not sure calibrating a thermometer, while probably useful and some good math, is not super exciting. So I'll try to find something a little bit more fun. Okay, so now we're going to talk about the unit of the calorie. And we're going to talk about this, that there is a calorie little c and a calorie big C. And we'll clarify that, like when you see calories on the side of a label, nutrition label, those are a little bit different than the calories I'm talking about right now. So sometimes chemists use a calorie to define heat instead of a joule. A calorie is the amount of heat, so it's an amount of heat, an amount of energy, because it's an energy measurement, necessary to warm 1 gram of water 1 degree Celsius. So it's that's what it is. It's also going to be, well, never mind, I'll stop. So the amount of heat necessary to raise 1 gram of water 1 degree Celsius. So start with the amount of heat to get yourself moving in the right direction with that sentence. And why? It says why do we even use a calorie? Why don't we just use joules? Scientists knew that they didn't always know that heat was just another form of energy. So they measured it and they defined it this way before they knew that it was energy, before that James Joule came around. All right, where are we at? Okay, and so we should be able to move between calories and joules. They should have some equivalency, right? Because they're both energy. And we do 1 calorie equals 4.184 joules. And that is something you should memorize. That's one you'll want to know. So it takes a little more than 4 joules to make a calorie. So the calorie is a bigger energy unit than a joule, just as you think about how to compare them. And then we talk about calories on a nutrition label. Is one of my children calling me?
Mom?
Yeah?
Are you on the phone?
No, I'm making a video for chemistry, and I'm about halfway done.
Okay, I have a question.
Can you ask it really quick? Because I'm like literally in the middle of a video, and I'm doing it on YouTube, so I can't really pause it.
Are you shopping to get some underwear for me?
Do you really want to ask about that on a YouTube video?
Is this YouTube?
Yeah.
Wait, you're a YouTuber?
No, well, I'm not a YouTuber, but I'm making, yes, I guess I am. Okay.
Like, what's your channel?
Wolf, quiet. I'll tell you later. Be quiet. Wolf wants to know if I'm a YouTuber now. I don't really think I'm going to count as a YouTuber. I'm probably not going to get like 5 million views, but if I get 5, that would be great. Okay. What are they saying here? Okay, calories on a nutrition label. So calories are, when we see calories, capital C, it's the amount of calories in a serving of a product. And so the question is, what is that? Is that the same as 4.184 joules? It is not. It's actually 1 calorie with a capital C when you see that. So if a food has, 500 calories in it, each of those calories is equal to 1,000 calories little c. So they define those as food calories and chemistry calories. That might be a good way to differentiate it in your brain instead of little c, capital C. So one food calorie that you see on a nutrition label is equal to 1,000 calories. So it would be the same as raising 1,000 grams of water 1 degree Celsius, right? Yes, make sure I was saying that right. So like it says on the average human body uses 2,500 food calories to do all its work in a day. So that would be enough energy to heat 2.5 million grams of water 1 degree Celsius. And as it says, it's pretty amazing that God's designed our bodies to do all that energy without overheating. So pretty amazing when you think about that's how much energy we use, because sometimes I think I do not do enough, and sometimes I don't do enough in a day to burn that many calories, and that's why we don't need to eat 2,500 calories unless we're actively walking up and down stairs and moving and walking during a given day. Hey, Wolf, I know you're trying to be silly, but it's just distracting. And I'll tell you what, not one of my chemistry students thinks that that's super funny. I promise you. Hey, Wolf, can you put on, please? Stop. Okay. So I really need you not just to stand here and distract me. It's really hard for me to keep my train of thought. You may listen. You cannot just stand over here and do a bunch of crazy things. I cannot think and concentrate on that. Excuse me. So let's look ahead here for a second. We're going to talk about measuring heat and how we measure heat. We talked about change in temperature. We're going to talk about a way to measure heat. So even though chemists have traditionally measured heat in calories, most of the time you're going to see joules. That's usually what we're going to use is joules. But as they say, occasionally they'll have used calories, so then you just have to use that calories to joules conversion, just like if you had 5,000 calories and then you would put 1 calorie equals 4.184 joules and multiply. It's just a conversion, just a unit conversion. So they'll probably give you those in some problems just to make sure you can practice and use those. So we're going to see a formula that looks like this. Let me write it down. It's a terrible whiteboard that I picked. It's kind of a one that looks like it hasn't gotten erased very well. So we have an equation that looks like this. Q is heat. M is the mass of the object. C represents the specific heat of the object, which we're going to talk about in a minute. And then change. Remember that triangle means change in temperature. So again, just a plug and chug kind of formula where we just have to grab all the different pieces to plug it in. And we'll talk about what specific heat is shortly. Let me see here. So they give us the equation. They give us any more in this section. When heat's given to an object, its temperature will increase as it absorbs that heat. And so if the temperature begins to rise, we can assume that object is absorbing heat. If it starts losing temperature, we can assume it's releasing or losing heat. And that's that temperature change that we're measuring. And that temperature increase or decrease should be in some way proportional to the amount of heat the object absorbs or releases, which it is. As change in temperature goes up, specific heat should go up just because of if this gets bigger, no matter what these are, if this gets bigger, then this will get bigger. Specific heat is always going to be the same for a specific, like water has a specific heat, silver has a specific heat. So that would stay the same. So as the mass gets bigger and the change in temperature gets bigger, there's more heat, which would hopefully make sense. So specific heat is a physical property, like density is a property of a substance. Specific heat is the amount of heat necessary to raise the temperature of a gram of a substance by 1 degree Celsius. Well, that should sound a little like, ding, oh, that sounds familiar. So please stop, honey. So a calorie says that's the amount of heat it takes to raise water, 1 gram of water, 1 degree Celsius. So 1 calorie or 4.184 joules is the specific heat of water. Baby, stop it. It's so distracting. I'm trying to talk about things that are not the most simple thing in the world. And you pulling my hair behind me is super distracting. So if you look in your book at table 12.1, it's on page 430. It gives the specific heat of several substances. And they give an example. If you put a piece of wood on a stove and you put a piece of metal on a stove, provided that wood didn't just start on fire, the metal will get hot faster than the wood. It's going to take less heat to raise that temperature. So for instance, if you compare, like water has a specific heat of 4.184 joules. So it takes a little over 4 joules to raise that 1 degree Celsius. But like copper's specific heat is 0.3851 joules. It only takes 0.3 joules. So if I apply 4 joules to water and copper, the water is going to raise just 1 degree Celsius, or 4.184 joules. The water is going to raise in a gram of each. The water will raise 1 degree Celsius. The copper at 0.3 would have risen 1, at 0.6 risen 2, at 0.9 risen 3 joules. So it's going to have more heat. It's going to, raise its temperature more with a lesser amount of heat. Does that make sense? It's how the temperature uses heat, I guess you could say. I feel like I'm not saying that very well. Let's see if there's anything. They give a really nice example, kind of like what I just said. But yeah, it's essentially just what I just said. But I wanted to see if there was something they said in here that makes it a little bit more clear. Yeah, just read that paragraph underneath the table. It's basically what I said. It's comparing gold and copper with different specific heats. Gold is also like 0.1. It's a lot less than even copper. So again, given 1 joule, every 0.1, that temperature is increasing of that gold versus it needs to get to at least 0.3 before it raises to 1 degree Celsius when you're talking about the copper. So these numbers are unique. So you don't have to memorize the whole chart, but you do want to know water. So 1 calorie is also the specific heat of, describes also the specific heat of water. So make sure you read through that if you didn't understand what I was talking about, which I could understand if you didn't. So, but at least you heard it. Read it again in the book and make sure that makes sense to you. What else do we see here? They have a long section on the next page talking about how they get to the units for a joule, but actually, or not for a joule, for specific heat. But actually, if you look, it's the amount of heat, joule, to raise the temperature once, because it's joules per grams times degrees Celsius. You can kind of see it from the definition. They talk about it like, it's kind of weird to me when they talk about we get the units so that it'll cancel out with everything else, but it's not exactly how we get them. It has to do with what it is, like the definition of it. I mean, we don't just get units, but then it works out that they cancel out because the formula works. I feel like it's so backwards to say that we get the units by just finding units that will cancel out with the units that we have there. That doesn't really seem fully correct to me, but again, I'm not the smartest person in the world. I could be wrong on that, but we also get the units because of what we're actually measuring. So that's that. All right. I'm not going through problems because they're kind of complicated that we're going to do those in class together. But I would encourage you, this was not new to me. I've heard of all these things before, but like I said, more physics related, and physics never comes back to my brain as easily as chemistry. It is still chemistry, but I had to kind of, okay, let me look through that problem and make sure I know what's going on here. And I would encourage you to do that too, even if you can't specifically feel like you could write it out yet, at least see if you can follow the steps of what they're doing. Okay, then we get to something called, I was gonna look up how to say this before I got on the video. Calorimetry. I think that's how you say it, a calorimeter and calorimetry. I'm pretty sure, I don't know how else you would say it. That's how I'm gonna say it. Sometimes there's just different ways. I had a lot of teachers that would say alveoli and teachers that said alveoli. Yeah, something in your lungs. Sometimes there's just different ways to pronounce it. I'm just gonna say this is my way to pronounce it. Okay, so a calorimeter is a way to measure change in heat of something. Let's see, so they're reminding us about the specific heat of water and talking about how specific heat is measured. Let's see, what are they talking about here? Sorry, I was just trying to see what all they're trying to explain to you here. They're talking about how you could measure the specific heat. Sorry, I feel like I read through this kind of quick last night, this part, because I did read it, but how is specific heat measured? And they look at that equation that we just talked about, that Q equals, the change in heat equals the mass times the specific heat times the change in temperature, and saying we need 3 different measurements because specific heat is heat. So how will we measure the specific heat? So we measure the mass of an object, its temperature change, and how much energy it has experienced. And we calculate heat with those measurements. So we can measure mass, right? That's easy. We can measure change in temperature with a thermometer. Oh, that's right, because we're talking about solids. I was like, I did read this. So that works really well to measure the change in heat. If it's a liquid, we could stick our thermometer in and measure that. But with a solid, that's a little bit more difficult. So we can say that if a solid sits in an environment long enough, it will be equal to the temperature in the environment. And so if it releases heat, then the environment's temperature is going to rise. It's going to absorb that. Well, if we're in a room, we're not going to be able to detect that. It's just going to be too diffused. So that's why we can use something where we make the environment smaller and something easier to measure. And so what we use is something called a calorimeter. And a calorimeter, or calorimetry, it's best if you just look at the picture on page 434. I could draw you a picture and I'll try to explain it to you, but the picture is much better. So you have a box, you have an insulated box, and it's filled with water and it has a little spot for a thermometer to go down in there, and a little stick to kind of stir things up to make sure the water's the heat's all distributed evenly. And so we can measure the change in heat. So we can measure let's say we take an object and we heat it up really hot and we put it in there, and we take that temperature, and then as that temperature changes, we take that temperature again and we get our change in temperature. So for instance, they give we'll get to the specifics because we have to look at a few things there, but sorry, I feel like I'm suddenly making no sense at all, and I apologize for that. I hate when I get a little distracted and when one of my kids and my thinking gets a little bit messed up. So they talk about a chemical reaction is carried out in a 5-gram calorimeter. I just want to explain it in terms of an example. I think that makes more sense. So that means as much the calorimeter weighs. The calorimeter has a specific heat. So the calorimeter itself, how much does it take to raise 1 gram of water, 1 degree Celsius in that calorimeter, and its specific heat is 1.95 joules per grams times degrees Celsius, and it's filled with 150 grams of water. We already know the specific heat of water, right? Hopefully 4.184 joules. If the temperature per grams times degrees Celsius, if the temperature of the water was 24 degrees Celsius, so the water's sitting there, it's 24 degrees Celsius with nothing in it, before the reaction took place, and it rose to 32 degrees Celsius by the end of the experiment, how much heat was released by the reaction. They don't really tell us what the reaction is. They just tell us that the heat started at this and then it rose to this. So it tells us that something happened that gave off heat, and we just want to see how much heat was released by that. And so then they give us an equation that looks like this. I think this will all make a lot more sense when we work the equations in class Monday, but it's definitely important that you've heard it before, just like last week. Oh, I was thinking about Emily's suggestion to do this at Starbucks. We could. I do think that's a fun idea. I need to clear it with all the moms, but I would say that everybody has to have watched the video. I wish I could see if you've watched it in full. I guess I would know when we got to Starbucks if you're just like, I have no idea what you're talking about. I don't think I've ever heard these terms before. So I can clear it with moms. We could take the video. Why not? That would be fun. We'll see. But definitely the requirement would be that you all have had, I need to see 5 views on that video. And if I don't see that, there's no way that we're going to go do that. So, okay, so the change in heat of the object, even though they're saying reaction, I think what they mean to say is the object that they put in there is going to be equal to the change in heat of the water plus the change in heat of the calorimeter. So this looks like this. I think it looks like a weird equation. This is negative, and it's negative because the temperature of the water was 24 and the water got higher. So if the water got higher, it absorbed heat. It had to have absorbed heat from that object that got put in there. So if the object gave off heat, if it got absorbed by the water, then the temperature of the object decreased, and that's why that's negative. Does that make sense, hopefully? So to find those things, to find the heat of the water, we're going to go back and use this equation that we saw earlier. Again, I'm not going to work through all that, but we take the mass of the water, specific heat of water, and the change in temperature. And the change in temperature is both the same for the water and the calorimeter. It went from 24 degrees to 32 degrees. It rose. So that's the specific heat of the water, if that was the one we were doing. And then we take that same equation and we do it for the calorimeter. Just giving you steps here mainly. Oops, left my E out of calorimeter. And that's still going to be mass times specific heat times change in temperature, okay? And so the mass of the calorimeter they gave us, it was 5 grams. The specific heat they gave us, the change in temperature is right there. So I plug all those things in, I add those together, and they give me a final amount of joules. So the heat of the calorimeter, or the energy, the heat is only 78 joules. It's just small. It's the water that's really absorbing that energy, and it's 5.0 times 10 to the third joules. So I add both of those together, and I find out the heat for both the water and the calorimeter, and it's negative 5,100 joules because of that negative Q. So I take that, it becomes something that looks like this, and then I just, solve like I would in algebra. I just can move that, basically dividing by -1, right? So I get a positive Q on this side and a negative 5,100 joules. So the amount of heat that was lost by the object that got placed in there was 5,100 joules, you could say. It went down, and the water absorbed 5,100 joules, the water and the calorimeter. So calorimetry is often used to determine the heat released by a chemical reaction. It can be used to determine the specific heat of an object. So we'll talk more about that in class. So I think that's enough for now. It's a little bit of a long process, but they have a lot of words in there, so it's not that bad. Let me see if there's anything else. Oh, they do note that sometimes the heat absorbed by the calorimeter is so small, it didn't even show up when we added to the heat absorbed by the water. Like it got lost because of significant figures. And so it says that often happens in calorimetry experiments, and so often we just disregard the heat absorbed by the calorimeter when doing those kinds of experiments. And it says that, I think they'll tell you. So if they want you to ignore it, you'll just set it equal to 0, so it just won't add anything into that total heat. And they say if they give you information about the calorimeter, then you should assume that it should be involved with it. If they don't give you any information about the calorimeter, then you can assume that it just got left out. Okay, I believe that's everything. It's really not a bad module. I think we're gonna be able to work through it pretty well. And there's kind of some complicated thoughts, maybe, if you're not used to thinking in a physics kind of way, that change in energy. And even I'm still thinking about that fire one because energy is work, and work is the force applied in a parallel motion. And I'm like, well, is it parallel in that fire? What's actually happening there? I know it's true. It's just a little beyond my thoughts. So if any of you are super smart in physics, feel free to answer that question. Like I said, I'm gonna play everything into Moodle this morning, and I need to get you guys information too about your project. I'm trying to decide if I throw that at you this week. Kind of curious, do you like to have a longer time to think about it or a short amount of time and just get it done? I don't know. Sometimes I like having a little bit longer time and planning what I'm going to do. I think I'm going to give it to you because there's some choices to make on what you want to do. It's actually what Mrs. Estes did, some options she gave, and I think she really did a nice job of emphasizing people's things they're good at, if they like to write or if they would rather do something hands-on, or however you like to work, that you could use that to present information and get the job done, but in a way that is more pleasant to you, hopefully. So we'll get that out there, but I'll get this week's assignments. You've got your videos to watch, lab write-up to finish, the extra practice problems for module 11. I think that's it. I'll think through that before I put that up, but I think that's everything. And then when you come in next week, hopefully everyone will watch the video and we'll work on your own problems and get everybody understanding this unit and kind of move on. So that's kind of how the weeks will flow, with the quizzes plugged in there as needed. Nisha, don't slam that pen down. It ruins the tip of it, baby. With the quizzes plugged in there in labs as they come up, don't slam it down. I think that's everything. You guys have a great day. I'm thankful for this schedule. It feels nicer to me too. I feel a little less stressed out, and I hope you do too. I hope you feel like you're getting adequate amount of time to practice things, hear things, ask questions, and
Oatmeal.
yes, I'm gonna get you some oatmeal in just one sec.
No,
Oh, here,
no.
you get to say hi because everybody feels like you're an installment on the chemistry videos. Can you say hi? No? Can you just say hi instead of no? Or you could just show your super special slap big end. All right, you guys take care. I'll talk to you later. Bye.